We've seen the implicit Euler method for a simple concrete model problem. The implicit Euler method is more complicated than the Euler method, but we've seen that the implicit Euler method comes with a superior performance, at least for that simple model problem. So it seems worthwhile to learn a bit more about the mathematics of the implicit Euler method. In this video, we discuss the mathematical background of the implicit Euler method, and then we also have a look at a few more examples. Let us recall the iteration formula for the explicit Euler method. uk plus 1 equal uk plus h times f of tk uk. At every iteration, the value uk has already been computed previously, or is given by the initial condition, and we compute the next time step using this iteration formula. In particular, we have an explicit formula how to compute uk plus 1. By contrast, the iteration formula for the algorithm that is known as implicit Euler method looks quite different in a small detail, and that small detail has grave consequences. The iteration formula for the implicit Euler method defines uk plus 1 by the equation uk plus 1 equal uk plus h times f of tk plus 1 uk plus 1. As you can clearly see, uk plus 1 appears on both sides of the equation. So this is not yet an explicit formula to compute uk plus 1. It's merely an equation that, as we hope, implicitly defines uk plus 1. Explicit Euler method in this context is just a different name for what we have called Euler method so far. This is only to contrast the normal Euler method more explicitly from the implicit Euler method. We can put this into the framework of nonlinear equations. Namely, we define uk plus 1 implicitly as a solution of the following equation with right-hand side 0, namely uk plus 1 minus uk minus h times f of tk plus 1 uk plus 1 equals 0. In that sense, we can define uk plus 1 as a root of some function g, defined by this equation here. Now we can assume that uk is already given from the previous iteration. We already know step size h, of course, and we know the next time step, tk plus 1. So in order to find uk plus 1, we need to find a root of that function g. We already know different ways to find roots of functions. For example, we can just throw the Newton method at that problem, and after a few iterations, hopefully it produces a solution to that equation. In many cases, however, we also have problem-dependent knowledge, so we know the concrete differential equation, and we can use that knowledge to actually compute uk plus 1 explicitly. We have already seen this in the previous example with the differential equation u prime of t equal minus alpha u of t. Before we proceed, I would like to emphasize this difference between the explicit Euler method and the implicit Euler method. In the explicit Euler method, we simply take our approximation uk at time step tk, plug this into the update formula for the Euler method, and that produces the approximation of u at the next time step, the approximation uk plus 1. So at every iteration of the Euler method, we perform some simple calculations. We feed in uk and we obtain uk plus 1. The iterations of the implicit Euler method are generally more complicated. Given the variable uk, which approximates u at time tk, we set up this equation, which implicitly defines uk plus 1, and then we need to run a sub-algorithm in order to find uk plus 1, at least approximately. This means that every iteration of the implicit Euler method, every iteration step might need a not quite trivial amount of computation by itself using an internal algorithm, such as the Newton method, the bisection method, or sometimes we need to use our ingenuity to reformulate this problem so that we have an explicit formula for uk plus 1. This really depends on the concrete problem. Okay, I would like to proceed first with some mathematical background for the implicit Euler method, which gives us some comparison with the explicit Euler method, and then we take a look at a few examples. As you hopefully remember, we have seen no less than 3 different ways to motivate the iteration formula for the Euler method. Namely, we had difference quotients, we had integration, and we had the Taylor series. For the sake of comparison, we do the very same thing also for the implicit Euler method now. Okay, let's get on with the first way to introduce the implicit Euler method. Similarly to the explicit Euler method, we start the discussion with difference quotients. We start again with the Cauchy problem, u prime of t equal f of t u of t, with the initial condition u of t naught equal u naught. So let us suppose that u is the solution to the Cauchy problem, and that u of t is already known, or at least known approximately. And going from there, we want to approximate u at time t plus h, where h is again the step size. Now for any time t and any step size h, you can take a look at the difference quotient, u at t plus h minus u at t divided by h, and that difference quotient can be seen as an approximation of the derivative of u at t plus h. So we have got this approximation u at t plus h minus u of t divided by h is approximately u prime of t plus h. Now we can rearrange this approximation and get that u at t plus h is roughly the same as u of t plus h times u prime of t plus h. And similar to the derivation of the explicit Euler method, I simply now use the differential equation in order to replace u prime by the right-hand side f. So I end up with the approximate identity u of t plus h being roughly the same as u of t plus h times f of t plus h u of t plus h. Now we see that this looks very similar to the explicit Euler method, except that on the right-hand side, f is taken at time t plus h with the value u at time t plus h. And in particular, u of t plus h appears on both sides of the equation. So all I've gotten so far is an identity that is satisfied by u of t plus h. The significance of that last approximate identity is as follows. If I already know u of t exactly, or most likely approximately, then I can act as if this last approximate relation is actually an identity, just as if, and then I can try to solve this equation for u of t plus h. If I manage to solve this, then the value I get for u of t plus h will be an approximation, hopefully a good approximation, for the true value of u of t plus h. Another mathematical background for the implicit Euler method is in numerical integration. So let us recall that u of t plus h equals u of t plus the integral of u prime from going from t up to t plus h. That integral, of course, might be very difficult to compute. So I can replace it by some numerical integration formula. In the explicit Euler method, we have taken u prime and evaluated it at t to get an approximate value for the integral. But this time, for the implicit Euler method, we take the value of u prime at t plus h at the right end of the time interval. And so we can say that this integral of u prime from t up to th is roughly the same as h times u prime of t plus h. That's just an approximation. And so again, we get this approximation u of t plus h being roughly the same as u of t plus h times u prime at t plus h. And plugging in u prime for the right-hand side of the differential equation, we get this approximate relation that leads us to the implicit Euler method. And finally, let's not forget about the Taylor series. For any time t, any step size h, we can take the first order Taylor polynomial of u around the time t plus h, and then use the Taylor theorem. And then use the Taylor theorem to get an expression for u of t. The identity that we get is u of t equal u of t plus h minus h times u prime of t plus h plus h squared over 2 times u prime prime of xi, where xi is taken from the interval between t and t plus h. So in some sense, I take the first order Taylor polynomial of u around time t plus h, and I use that to go back in time to get an approximation of u at time t. That approximation is very accurate. The remainder term here is h over 2 times u prime prime of xi. The xi is from this time interval t up to t plus h. That is really just a Taylor polynomial, and you might pause the video to take a look at it before we proceed. Now, heuristically, if h is small, then this last term involving h squared might be very small too. It will most likely go quadratically to 0 as h gets smaller and smaller. So we get the approximate relation that u of t is roughly the same as u of t plus h minus h times u prime of t plus h. Okay, now, similar as before, we can do some algebraic manipulations and plug in the right-hand side of the differential equation in order to get rid of u prime. And so again, we get the approximate relation u of t plus h is roughly the same as u of t plus h times f of th u of t plus h. This approximate relation, for which we have seen now 3 mathematical backgrounds, leads us to the implicit Euler method, which looks quite similar to the explicit Euler method, except that now the iterates are computed with a different procedure. We've got a sequence of discrete time steps starting with t0, then t1 is defined as t0 plus h, t2 is defined as t0 plus 2h, and so on. Tk is defined as t0 plus k times h. You've got a sequence of discrete time steps with a step size h. You approximate u at each of those discrete time steps. For example, at time t0, we already know the exact value of u from the initial condition u0. We compute an approximation u1 of u at time t1, an approximation u2 of u at time t2, etc., etc. And generally, we compute an approximation uk of u at time tk. Each of those approximations is obtained as follows. Namely, suppose that I already have the approximation uk corresponding to the time step tk, then I get the approximation uk plus 1 corresponding to the time step tk plus 1 by solving the equation uk plus 1 equal uk plus h times f tk plus 1 uk plus 1. Let me emphasize that the unknown variable here is uk plus 1. And we assume that we already know uk from the previous iteration, and of course we already know f, we know h, step size, and we know the time tk plus 1. In general, uk plus 1 is always calculated by some nonlinear solver. Sometimes the differential equation has some special structure that we can use to actually get an explicit formula for uk plus 1, but that is highly problem dependent. Another problem in general is that we need to make sure that uk plus 1 is uniquely defined. In other words, we need to make sure that a solution uk plus 1 actually exists to that equation. And even if it exists, we need to make sure that it is unique. So when comparing the explicit Euler method and the implicit Euler method, we can say that the implicit Euler method has certain advantages for some particular ordinary differential equations. But the price that we pay is that at each time step, we need to do a more complicated calculation to get the next iterate. For the explicit Euler method, we just need to do some straightforward calculations. But in the case of the implicit Euler method, we need to solve perhaps nonlinear system of equations. Solving that nonlinear systems of equations typically entails a set algorithm that we need to perform at each time step. And then again, we actually also need to make sure that the solution uk plus 1 is actually defined, and in particular is also uniquely defined. So we see that the implicit Euler method does have advantages, but those advantages do not come for free. The sequence of calculations that we perform with the implicit Euler method can also be summarized as follows. So we start with the initial condition u0, which is already known. In the next time step, given u0, we solve the equation u1 equal u0 plus h times f of t1 u1 for the unknown variable u1. And then in the next time step, having computed u1, we solve the equation u2 equal u1 plus h times f of t2 u2 for the unknown variable u2, and so on and so on. In general, having computed uk already, we solve the equation uk plus 1 equal uk plus h times f at tk plus 1 uk plus 1 for the unknown variable uk plus 1. Each of those time steps involves the solution of a nonlinear equation or system of equations. In order to get a feel for that, let's take a look at an example, namely the Cauchy problem that we've seen earlier. U prime of t is equal minus alpha times u of t. We already know u0 from the initial condition. In the next time step, we compute u1 equal u0 plus h times u1. We solve that equation for u1. Having computed u1 in that manner, we solve the equation u2 equal u1 plus h times u2 for the unknown variable u2. Then, having computed u2, we solve the equation u3 equal u2 plus h times u3 for the unknown variable u3. And in general, having computed uk, we solve the equation uk plus 1 equal uk plus h times uk for the unknown variable uk plus 1. In the case of that particular differential equation, the solution procedure at each time step can be written down in a very simple manner. Namely, u1 is just equal 1 plus alpha times h inverse times u0. Similarly, u2 is equal 1 plus alpha times h inverse times u1. u3 is 1 plus alpha times h inverse times u2. And in general, uk plus 1 can be computed from uk simply by calculating 1 plus alpha times h to the minus 1 times uk. So here we can use the particular structure of the differential equation to simplify the calculation at every time step of the implicit Euler method. Now, to get some more practice, let's take a look at the Cauchy problem u prime of t equals 3 times u of t plus sine of t to the square. Again, we know u0 from the initial condition. And then we solve u1 equal u0 plus h times v u1 plus sine of t1 square for the unknown u1. Then we solve u2 equal u1 plus h times v u2 plus sine of t2 to the square for the unknown u2. We solve u3 equal u2 plus h times v u3 plus sine of t3 to the square for the unknown u3. And generally, we solve uk plus 1 equal uk plus h times sp uk plus 1 plus sine of tk plus 1 to the square for the unknown uk plus 1. The variable uk is already known from the previous calculation, and we use that value to define this equation, and then we solve that equation for uk plus 1. In fact, we can again use the special structure of the differential equation to simplify the solution procedure. Namely, with some algebraic manipulations, we see that uk plus 1 equals 1 minus 3 times h to the minus 1 multiplied by uk plus h times sine of tk plus 1 to the square. All the terms on the right-hand side of that last equation are already known, and so we can just plug in uk to get immediately uk plus 1. Let's do one more example. Let's take a look at the Cauchy problem u prime of t equal minus 2 times u of t minus exponential of minus 4 times t plus 2. The value u naught is already known, and generally, if the value uk is already known, then we set up the equation uk plus 1 equal uk plus h times minus 2 times uk plus 1 minus the exponential of minus 4 times tk plus 1 plus 2, and solve that equation for the unknown uk plus 1. The special structure of the differential equation again allows us to simplify that formula a bit. And so some algebraic manipulations tell us that uk plus 1 equals 1 plus 2h to the inverse times uk minus h times exponential minus 4 tk plus 1 plus 2 times h. So using the special structure of the differential equation, I in fact get an explicit calculation for uk plus 1. I simply plug in uk on the right-hand side, and some calculations produce uk plus 1.